So I'm delighted to talk to you today about recent progress in global mantle tomography. And I first want to acknowledge the work of my students who have done most of the work that I'm going to be presenting today. These are students and postdocs from UC Berkeley, it turns out. So mantle tomography started 30 years ago. This is an illustration of the first complete shear velocity model, tomographic model, developed by Woodhouse-Jaworski in 1984 for the upper mantle. It's showing the shear velocity at 100 kilometers depth. And it's an opportunity to first remind you the color scale that we use. These are perturbations with respect to the average at this depth, the global average at this depth. Red colors mean that the shear velocity is lower than average. So interpreted very naively, this means hotter regions than average. And blue colors mean faster than average velocities, that is colder than average. What is striking in this figure is that the main tectonic kind of units are already present, reflected in this map at 100 kilometers depth. So you can see the ridge system manifested by lower than average velocity, hot material coming up. You can also see the back arcs. And then you can see the cold cores of the continents, here Australia, the cratons in North America, Antarctica. And interestingly, also the cooling of the Pacific plate as you go further away from the ridge. So even though this image was very kind of long wavelength and not very sharp, it already had important an important role in confirming once the plate tectonics and the fact that in the first few hundreds of kilometers of the Earth, the distribution of heterogeneity is governed by plate tectonics. This is an image from the same group at Harvard, but almost, 25 years later, which shows the progress in these large-scale imaging done with relatively standard techniques. And you can see that there are more details in all these features, but the large-scale features essentially are the same. So in the last 30 years, there has been progress in imaging. And we have, I just wanted to start by kind of reminding you what the main kind of features of the mantle structures that have been found and on which all the groups that are doing tomography basically agree. So this is the same map I showed at 100 kilometers. If we go deeper, at 600 kilometers, this pattern of plate tectonics has already disappeared, and what's left is fast velocities here in Western Pacific and South America that manifest subduction zones, which have also been imaged in more detail by more regional travel time tomography, or focused on these subduction zones where you have very good illuminations by seismic waves due to the presence of many earthquakes and many stations. And so these images now are much more precise and show the behavior of the subduction zones as they go down into the mantle. Here, ponding at 600 kilometers depth in these regions, at the 660, at the limit between the upper and the lower mantle. As you go deeper, the image changes again, and the fast velocity, strikingly fast velocities that come out of this rather short wavelength, not very clear picture, are only some regions in which the slabs actually penetrate deeper. And as Fukai and Obayashi pointed out a couple of years ago, there are these regions where the slabs pond deeper. This is 1,000 kilometers depth. I will return to this later. And then as you go deeper to the bottom of the mantle, this is 2,800 kilometers depth, so 100 kilometers above the core-mantle boundary, the pattern has changed completely and has been replaced by the well-known features with low velocity zones, large low shear velocity provinces, which is terrible name, but it's still what we use, centered on the Pacific and under Africa, and surrounded by a ring of fast velocities, which is generally thought as being the graveyard of slabs, as it is located under the subduction zones, even integrated over the last 200 million years. And this picture at the base of the mantle is very striking and is really well resolved. I wanted to show you at the large scale. It shows a relatively red kind of distribution of heterogeneities dominated by long wavelengths, but many the models that have been developed in the last 10 years actually agree on not only this pattern, the presence of these large low shear velocity provinces, but even on their borders. What's here is shown a comparison of 5 models, recent shear wave velocity tomographic models, where basically it's a voting map, where if every model thinks the velocity is lower than average, it will be red. If every model thinks, every model shows that the velocity is faster than average, it will be blue, and you will notice how it kind of emphasizes the large low shear velocity provinces, but also their borders that are very well defined at a shorter scale. And then there is this anomaly here, intriguing anomaly, which we call the Perm anomaly, because it's located near the place where the Permian, where it's located near the town of Perm, but it also happens to be near where the Permian traps erupted. So the large-scale structure is now quite well established at the global scale, but of course we're interested in other objects, such as, for example, the origin of hotspots. So hotspots such as Hawaii, with their characteristic age progression here in million of years in the direction of the plate motion of the Pacific plate. And as you know, a theory for this, the occurrence of these hotspots in the middle of tectonic plates was proposed by Tuzo-Wilson first and then by Morgan, that they proposed that these were fixed plumes in some boundary layer inside the Earth, which provided upwellings, fixed upwellings that over which the plates move. And Morgan's contribution was to suggest that this boundary layer was at the core-mantle boundary. There are other, of course, indications that hotspot volcanism is different from plate boundary volcanism. For example, isotopic composition of trace elements shows very distinct features of hotspot volcanism compared to mid-ocean ridge basalts, which has prompted the geochemist to suggest that there are different reservoirs of chemical heterogeneity in the mantle. There is also evidence from numerical modeling and laboratory experiments for the existence of mantle plumes, in convective systems, where here the box, the fluid is heated from below, and as a function of time, you see these rising plumes that have characteristic shapes with narrow stems and fat heads. This is a numerical experiment, but it's also visible in the laboratory. And if you transpose these experiments to scale them to the Earth's mantle, you expect that the stems of these plumes would be very thin, maybe 100 to 200 kilometers in diameter. So then the question becomes, can we ever resolve them in tomography? And this has been, of course, a debate that you all know, whether the hotspot volcanoes are due to mantle plumes or whether they are nearly lithospheric kind of phenomena, shallow phenomena. So I will now spend just a little time on emphasizing 2 fundamental principles of tomography. So the first one is that in order to resolve structures, it's a very simple principle. You need to have sampling. You need to have illumination from many different directions in order to resolve an anomaly. Here it's shown as a slow anomaly embedded in a cold, fast anomalies. You really need to have many crossing paths to be able to determine what is the strength of the anomaly and its geographical extent. So that's the first the first principle. And of course, it's a challenge in the oceans because we don't have many, in ocean basins where many of the hotspots volcanism resides, we don't have many seismic stations and we don't have many earthquakes to play with. The other principle is that, in fact, when you have a low velocity body, such as a plume that you want to resolve, it's a challenge for seismology because if you use standard techniques that are based on using the first arrival ring waves, because as you think about it, the wave that goes through the low velocity body actually arrives later than the wave that goes around it. So if you only focus on the first arrival, the sort of ray theoretical infinite frequency arrival, you will miss this low velocity body, or you will image it, but not in a very precise way. So in order to really kind of be able to image these low velocity bodies that we are looking for, you need to consider the whole waveform and not only the first arrival. So there have been attempts to do that, and the most recent one, which is now 10 years old, is the travel time tomography of the Princeton group led by Husnoleh, who, this is like from one of the review papers by Knowledge, showing, this caused a lot of excitement, the presence of low velocity conduits under some of these, or many of these hotspot volcanoes. And the big kind of point that they were making is that they were using so-called broadband kernels, the famous banana donut kernels, which allowed them to consider the broadband character of the waves that are recorded. However, these are still based on the distribution of station and earthquakes that we have to work with, and on travel times. And there was, of course, a lot of skepticism as to whether, these features here, low velocity features, are really continuous, or you have to believe in it to see it. So, in order to help the distribution of stations and earthquake, which is a challenge in ocean basins, such as, for example, under Hawaii, there have been efforts, and there are still more efforts ongoing, to try and increase the aperture of the arrays that are looking into the mantle under the plumes. And this is an example for Hawaii by Wolf et al., who installed at great effort several experiments to install ocean bottom stations around Hawaii, and therefore get a little bit of a broader view of the deeper mantle. And so these are two cross sections from their models, and you can see very clearly in the upper mantle, the uppermost 200 kilometers of the mantle, this very strong low velocity zone surrounded by some fast velocity zones, and then a tail here. But again, skeptics would say, well, the tail may not be really well resolved because there is no crossing ray path in the lower mantle, so you cannot really determine, there could be smearing of these features in the lower mantle. So how do we remedy that? Well, first of all, seismograms are very rich in information. There are many different waves, and we can if we could use all of the seismogram in tomography, then we could take advantage of many different waves bouncing around the mantle and providing additional information, additional illumination to remedy the fact that the distribution of stations and receivers is not good enough. The other thing is that if you look closer, you can see that in the waveforms, you not only have the main phases, but you have what we call the coda of the main phases, the part of the waveform that is behind the first arrival. And I want to show you an illustration here. This is a synthetic experiment where we have put a a hypothetical plume here in the middle of the Pacific. It is about 400 kilometers thick, I think, and it goes all the way from the surface to the core-mantle boundary. And we've computed synthetics using the numerical codes that we now have at our disposal, that I will talk about a little bit later. And we compare the seismograms without the plume, so in a 1D spherically symmetric model, with the one with the plume. The plume has strength 6%, low velocity. And on the left, you'll see the seismogram itself. The black is without the plume, the red is with the plume, and here is the difference between the seismograms to emphasize the difference. Now, this is the path is far away from the plume, so you don't see much of a difference between the seismograms. You still see a little bit. Here, this is the S-diffracted wave, which travels along the core-mantle boundary, so it samples the base of the plume. And you can see there is some difference, which is not very strong. But as you go slightly closer, you can see that even though you're not within the plume yet, you can see a large difference between the codas here, the red and the blue. You can see the difference of the S-diffracted, but also SS, which are waves that bounce off the surface of the Earth in this. And then if you go inside through the plume, you also see some differences, but you have to go a little bit further into the sense. So the idea is then trying to exploit the information contained in full seismogram. And so the idea is then to take a data that it will be now the whole waveform, the whole registered seismogram from some earthquake to some station, and then compare it with synthetics computed in a 3D model. Until recently, computing these synthetics was a challenge and could be done only very approximately using primarily normal mode perturbation theory. I won't go into the details, but in recent times, we have at our disposal the so-called spectral element method, which is well adapted to computations in spherical symmetry and which has, in fact, been kind of ported to the case of the global Earth here at IPG by Jean-Pierre Villotte and his students. And so we can compare this to the real seismograms and interpret the difference in terms of improving the 3D model. The advantage of using this method, it is very accurate. You can have a model that has any size of heterogeneity, any wavelengths, and therefore this is the difference here. You're pretty much free of the theoretical assumptions in calculating the wave field. There are disadvantages. The computation time is very long. This is a numerical method, and it increases with the frequency to the cube. There are also conditions in the time step, so that if you have like the crust, now we have to worry about the crust. Global tomographers until recently just made crustal corrections without really thinking about it much, but now we have to really make sure we do it right. And if you have thin, slow layers in the crust, that slows down the computations because of a condition which relates the slowest velocities to the time steps that you have to use. And then, of course, this is a very nonlinear problem. You need many iterations. You need hundreds of events to be able to improve imaging. So much for a kind of technical background. I'm now going to show you some results. And basically, the results of 3 generations of tomographic models, and I wanted to acknowledge the authors of these models. First, an upper mantle model, which was determined with relatively long periods, because again, of these computational challenges, we have been progressing from long periods to short periods. And then extended to the whole mantle, including waveforms to shorter periods, which allows to separate what we call body wave packets in the seismogram. So no more technical details, but just some nice pictures. So first of all, the upper mantle, I will not spend much time on it because I've already talked about this here at IPG, but the kind of salient features of the upper mantle models is the presence at depths basically in the upper mantle, but around 250 kilometers depth most clearly, of elongated structures here in the ocean basins, here you see in the Pacific, that are elongated in the direction of absolute plate motion. And just to mention that these directions of absolute plate motions do not correspond to the directions of paths that we have across the Pacific, so this is not an artifact of the path distribution. If you look in cross-sections, depth cross-sections, 1 to 3, and this is a map showing relative velocities with respect to the average, and now I'm going to change colors and show absolute velocities just to emphasize the differences in depth. So these are now absolute velocities, so in kilometers per second, with the fast ones in blue, slow ones in red, showing this periodicity in these features. So what you see here is at 100 kilometers, you see the well-known low velocity zone of the upper mantle, but then beneath it, you see these kind of tongues of low velocities, where the velocity is as low at 300 kilometers as it is between these features in the low velocity zone. And they extend to depths in excess of 300 kilometers across the Pacific, but also in other regions. So this is a view from, if you're standing, say, on the East Pacific Rise, looking to the west, and you can see these same features here, emphasizing just the low velocity structure, kind of periodically extending deeper into the upper mantle. And then beneath it, you see that the pattern changes and is replaced by columns of low velocity that seem to be associated with hotspot volcanoes, which are indicated here by the green cones. This is Hawaii, and these are the South Pacific superswell volcanoes. So this kind of is interesting to kind of reminisce about the model proposed by Richter and Parsons in 1975, the so-called Richter rules, which correspond exactly to this alignment with the motion of the overriding plate. And the scale here would indicate a scale. This is in these models, which are in constant viscosity, the horizontal and vertical scale is the same, and the separation here between low and high velocity is about 1,000 kilometers, so they might be extending down to 1,000 kilometers. I would also point out that these features are not only seen in the seismic tomography, but they seem to be associated with a signal in the geoid. This is work here at IPG by Hein et al., who did a directional wavelet analysis of the geoid, showing that there is a lot of energy at a wavelength of about 1,800 kilometers. This is 1,000 kilometers between fast and slow, so 2,000 kilometers between the minima. And the black lines here are the same black lines here in the direction of absolute plate motion, but focusing on the Pacific Basin, there seems to be an intriguing relationship kind of indicating the dynamic origin of these features. I'm not going to talk about this anymore. It's something we're kind of investigating further with Isabelle Panet at the moment. But it's kind of inspired the idea that perhaps these features are due to a combination of secondary scale convection in the upper mantle, a la Richter rolls, and low viscosity kind of fingering from injection of low velocity fluid from deep plumes of low viscosity into a slightly higher viscosity layer. So that's for the upper mantle. Let's now look at the lower mantle. So the salient features of our model are these very strong conduits that we see under a large number of hotspot volcanoes. Here is just the first example shown across the Pacific. This is the location of the depth cross-sections. The green dots are the hotspots, also indicated by triangles here. And these are two different cross-sections, but not very far from each other. This one goes through McDonald, this one goes through Pitcairn. And you can see these very broad, very strong low-velocity columns extending from the core-mantle boundary to about 100 kilometers depth, and something happens to them. I will discuss this a little bit later. What you can see, though, here, that this is unique. This is like half of the world. This is almost 180 degrees in the length of the cross-section, and this is the only feature like this in here. There are other very small low velocity regions, and maybe there is something under Yellowstone, but if there is, it is of a different nature than these features. Now, I want to compare this with a model that is very frequently cited, the S40RTS from Ritsema and his colleagues, determined using more classical approach with travel times of different types of waves. And you can see that, in fact, these two models are not incompatible. We already see these features in this model. The only difference is now we can really see them much more clearly, but if you look in detail, you even see the deflection here in McDonald at 1,000 kilometers and at Pitcairn. So this is not just taken out of a hat, it is really something incremental, maybe progress in our ability to resolve structure in the mantle. If you look only at these, skeptics would say, well, you have yellow here, you have yellow here, how do you really know that this is a continuous feature? But now I think we have this documented. And so now these are the two I showed before in our model. This is one under Samoa, and this is a cross-section in different directions. This is one east-west, which shows three of them, Samoa, Tahiti, and the Marquesas. And to tie into what I showed before for the upper mantle, this is the upper mantle part of it, where you can see this kind of then interacting with the more horizontally elongated structures in the uppermost mantle. So that's one thing. You can see at 1,000 kilometers, things seem to be narrowing down, and we don't resolve them as well, just because we're still working on improving resolution. The other thing I wanted to point out here is in the upper mantle at Pitcairn, if you look, if you look in the upper mantle, in the down to 600 kilometers, you can see these alternating zones of high and low velocities, which are the same as we saw before from these fingers that I showed in the upper mantle, and that are clearly, you see these features in many of these cross-sections manifesting the secondary scale convection in the upper mantle. So you see these kind of features also in the Atlantic. These are examples. Cape Verde, you lose it at 1,000 kilometers, but it's probably there, just thinner. Canary, you can see the deflection very clearly. See it in Iceland, and in fact in Iceland, we can compare this model to a regional model also developed using these new techniques of waveform modeling using the spectral element method, but only regional for the upper mantle by Rickers and others, showing the good agreement on the kind of deflection here at about 1,000, 1,200 kilometers of these features with, under Iceland. So, to summarize these features in our model, we have kind of classified the features, we looked at the whole model and classified it, and basically classified in terms of what we can really very well resolve. These, we call them primary plumes, the black ones. Those that are perhaps not as clear, but still clear, we are gray. And there is only one here under the Indonesian subduction zone that is not associated with any hotspot at the surface. However, there is evidence in this region, my colleagues in geochemistry tell me, for kind of hotspot signature of lavas in this region. So it may be that this feature in the lower mantle is being deflected or kind of perturbed by the presence of the slab in this region. But the main point here is that all of these features are actually overlying the large low shear velocity provinces, which are shown here in the background in our model at 2,800 kilometers. And the other hotspots, which are indicated here in green from the compilation of Steinberger, do not have corresponding features. So this is also interesting and leads us to kind of make some comments about the large low shear velocity provinces. You may find that this structure looks a little bit spotty, but in fact, this is actually well resolved, as shown by some kind of synthetic tests that we did, where we assumed that the large low shear velocity province may extend in a kind of block continuous feature from the core-mantle boundary to close to 1,200 kilometers, I think, in this case. So these are cross-section views. These are views at different depths of the input model, and then we pass it through the last iteration of our inversion, and it's like a checkerboard test, if you want. We can discuss the complete validity of this, but it is what we can do easily without spending months redoing the calculations. And you can see that we can resolve these features quite well. I mean, we would resolve a continuous feature if it was extending like this in a block. So the fact that we see isolated conduits is really real. They also, even here, we can also have some resolution in depth. So if the large low shear velocity provinces extended up to 2,000 kilometers depth, so maybe the first 900 kilometers from the core-mantle boundary, we would also be able to resolve the difference between this and that. So keep that in mind as I go on to explain my current views on the large low shear velocity provinces. In any case, they are not large blocks that extend uniformly from the core-mantle boundary throughout the lower mantle. So other characteristics of these features, well, first of all, they're very broad. They're not the thin features that one would expect from laboratory experiments. So one can ask the question, is this a problem of resolution or is this real? So we also have done some tests, and this is an input model which extends from the core-mantle boundary to 1,000 kilometers depth. Input plume, here it is 400 kilometers wide and a shear velocity reduction of 2%. Passing through our modeling, we would get something extremely weak, 0.5%, and broadened. So there is likely broadening, but either the plumes are extremely hot, they would have to be, if they are 200 kilometers thin and we can see them, they would have to be at least 1,500 degrees hotter than average, which seems extreme, or they do have some breadth to them, most likely in excess of 500 kilometers in diameters, which is also what actually already Hussenollet suggested from his studies 10 years ago. So most likely they're not just purely thermal plumes, and there might be thermochemical plumes, as here shown from this paper by Lin and Van Kekkel, where you see the difference between an almost purely thermal plume with one that is grounded on a layer of heterogeneous denser layer, which is shown in white here. The white is the compositional heterogeneity, and which shows this kind of different morphology of plumes with some areas that are quite fatter. And the other aspect of this is that the quasi-vertical from the core-mantle boundary to the 1,000 kilometers depth. So, and then in the upper part of the mantle, there's often offset. So there seems to be something going on at 1,000 kilometers, right here. And one point I'd like to make is that there is no evidence, no strong evidence for mantle wind at a depth in the lower mantle, in the lower 2,000 kilometers of the mantle. So that models that kind of try to link this to geodynamical models with mantle wind in the whole mantle, I think, are not really correct, and that if there is mantle wind, it should be limited to the upper 1,000 kilometers. The other thing is this deflection at 1,000 kilometers, which is reminiscent of laboratory experiments here from Farnetani and Samuel 10 years ago, showing that if you have a change in viscosity, here it was put at 660 kilometers, you will change the morphology, you will have deflection and narrowing of plumes in the lower viscosity region in the upper mantle. So this is, of course, to be kind of confronted with what happens in the fast velocity zones. It's kind of fascinating that you actually have, we have this idea that slabs pond at 660 kilometers, but recent images indicate that in some regions they actually pond also at 1,000 kilometers. So here, in particular, this is Fiji Tonga, and this is in Western Java, also showing ponding not at 660, but at 1,000 kilometers. And in fact, if you look closely, this is something that we could have seen already 20 years ago, because if you look at the longest wavelength of structure, which has been resolved for the last 20 years, you already see this. So this is a slide which I'm not sure I want to spend too much time on. It's sometimes difficult to understand, but these are depth correlation functions. So you basically take a map at a particular depth, and you try to correlate the map with the map at a different depth. You get a correlation coefficient, and you plot it. So what this shows is, for example, how the structure at 1,000 kilometers depth here is correlated with the structure in the transition zone. And you can see these are wavelengths. This is the longest wavelengths, this spherical harmonics 1 to 3. You can see a decorrelation, right? Blue means decorrelation, red means good correlation. The lower mantle, deeper than 1,000 kilometers, is quite well correlated at these wavelengths, whereas there is a clear decoloration that's happening at about 1,000 kilometers. And these are two models. This is the P model of Kobayashi and Fukao. This is our upper mantle model, but if I showed you this in any other tomographic model, you would see the same. And in fact, if you filter the models at what we call degree 2, so the longest wavelengths of heterogeneity, and we're comparing here our current model, sophisticated model developed with the spectral element method, with two more classical models, this one from Harvard, this one from Ritsema et al. You can see this difference in the planform of these long wavelengths between the first 300 kilometers, the next chunk of the mantle down to 1,000 kilometers. And then there's a shift from, if you compare what you see here to the last 2,000 kilometers, so the lower mantle. You see this shift in phase, right? The blue, the maxima are shifted with respect to each other. So again, this is interesting because we never saw this, but it is pretty clear even in the very standard models. So finally, going back to these plumes, there is another aspect of this, is that they are rooted in very low shear velocities. You can see all of these have more pronounced low velocity regions right at their base near the core-mantle boundary. So for the last part of my talk, I'm going to shift and talk about ultra-low velocity zone. I'm anticipating on what I'm going to say. The idea is that perhaps these roots of these mantle conduits or plumes, if you want to call them plumes, contain ultra-low velocity zones. In fact, there is evidence for this, which I will show. So what are ultra-low velocity zones? Ultra-low velocity zones are localized regions near the core-mantle boundary that have been found not by tomography, because tomography cannot resolve them yet. Because of just the period and the distribution of the data, we cannot really resolve the ultra-low velocity zone. They are very thin. They don't extend more than 40 kilometers and many places less above the core-mantle boundary, but they have very strong reductions in shear velocity and in P velocity, and there is also some evidence that they might correspond to a density increase. And so they are very kind of intriguing features that have generated a lot of debate as to what their nature is. They cannot be explained just by thermal effects. And the two competing hypotheses is whether they are chunks of solid material that is enriched in iron, which would explain the velocity reduction. And the other hypothesis is that they are due to partial melting, which could also, at the same time, represent material enriched in iron. Note that the distribution, this is kind of, I don't really like this picture, but I show it because it's kind of illustrates the issue well, is these are kind of based on Fresnel zones, which I don't very much like the idea, but it shows that most of the ultra-low velocities found are in the vicinity, so far, in the vicinity or inside the large low shear velocity provinces. And there have been some hints in the literature, but based on basically correlations that have been also controversial, that there is an association with where they are ultra-low velocity zones and where there are hotspots. Now I will show you some examples of recent work under Hawaii, under Samoa, and under Iceland, where we and others have found really large ultra-low velocity zones. So the first study, and this is now not tomography, this is forward modeling. So you take some waveforms from seismic waveforms. Here, this is an earthquake here in the Western Pacific, observed at the dense US array network in North America. The waves go, they are diffracted waves that sample the green portions here near the core-mantle boundary in the vicinity of Hawaii. And we're looking at observed waveforms in a very narrow band, so relatively short periods, inaccessible with waveform tomography yet, at least not quite yet, where you show, as a function of azimuth, as you go from northern to southern records, you can see a very strong difference in these waveforms. This is a comparison of what would be predicted from a tomographic model, even our latest tomographic model, where you don't see these features. I note this decrease in the amplitude of the main phase associated with what we call a post-cursor, a very strong post-cursor that has a move out. You can't see it very well here. And in order to explain this, we introduced, this is work of my graduate student Zane Kotar, a very simple model of a cylindrical ultra-low velocity zone with a height of 25 kilometers, a diameter of 800 kilometers, which is very large for an ultra-low velocity zone, and a velocity, shear wave velocity reduction of 20%. The idea here is that this post-cursor is due to this deflection of the rays, of the paths of the waves around this diffracting point. Now, this happens to be right at the root of Hawaii, of the Hawaiian plume, as we later determined from our tomographic model. So this was already intriguing because this was, for the first time, you could really connect an ultra-low velocity zone, happens to be really large, to a plume conduit under, you could do the connection through the mantle from what you see at the core-mantle boundary and what you see at the top. Turns out others, this is work by Thorne and others, also found a very large ultra-low velocity zone under Samoa, corresponding to this patch of very low shear velocity, using other techniques that I will not, but also forward modeling of waveforms. And finally, I'd like to spend just a little time on a study of Hawaii that we completed recently, where, Iceland, which we completed recently. This is a cross-section across the Iceland plume, which we resolve, perhaps a little weakly, but we resolve it. And we're going to be looking at, again, diffracted waves. These are the theoretical wave paths of these diffracted waves, showing how their paths as a function of epicentral distance. For comparison, this is the SKS wave, which goes through the core. And the special thing about this study is that we were able to find many crossing paths, so earthquakes that illuminated this feature from the southwest to the northeast, and earthquakes that illuminated this feature in different ways from the southeast to the northwest. Whereas in these previous studies, there was only one corridor, so you could find a model that fits the data, but you couldn't really determine the shape. What we did, so this is just one example, so one earthquake here shown recorded at a bunch of US array stations, and again the waveforms as a function of azimuth, they're color-coded here, so the blue are the southernmost, the red are the northernmost. This is the location of the what we actually found as a ultra-low velocity zone to explain these features, but just pay attention to the waveforms. Again, you see these features with the decreased amplitude and a very strong post-cursors in a particular range of azimuths. This is the line going right through the middle of this zone. And there is also another feature which is these ripples, sort of a move out. It kind of connects with this thing. It's a move out, like a diffracting pattern that is visible in the data. you can't explain it with a tomographic model. Tomographic model will give you maybe a slight travel time delay, you can barely see it. In order to explain this, we introduced again a simple model, a simple cylindrical model of an ultra-low velocity zone, and we're able to explain these features quite well. And this ultra-low zone is again very wide. It is 800 kilometers in diameter. It's thinner than the one in Hawaii, only 15 kilometers. And it explains the data very well without, trying very hard to do complicated model, a cylindrical model. What's interesting about it is that with just one event, we cannot really tell that it's cylindrical. We could have elongated elliptical shape or more complex shape. But with the availability of data from other azimuths showing also these features that are not explained by the tomographic model shown here on the right, but that are well explained by a simple model, what is striking is that the same model that works for one event works for other events that are oriented in different ways. And so if we kind of bring this back together and rotate the positions of the events, for each of them we have a limited azimuth range of observation, but if we bring them all together, we can actually reconstruct the diffraction pattern. And the interesting part is that we can explain all of these with the same model that has a circular base. So this indicates that there is the ultra-low velocity zone has, to first order, is axisymmetric. And to me, that really points to a nature of the ultra-low velocity zone that is due to partial melting rather than a solid inclusion, which would be hard to explain why it would be both so regular in shape and located right under the plumes. So this leads to this very poor cartoon, but kind of summarizing we're not very good at cartoons, but anyway. So basically what I've shown you is that we have different features in the top 1,000 kilometers of the mantle that are kind of starting to come out of the slightly more resolving tomography with probably more vigorous convection just due to lower viscosity. And then a very stagnant lower mantle with only kind of discrete, isolated conduits where the dynamics is concentrated and probably not much going on in between. Slabs kind of falling slowly down to the core-mantle boundary. And then under at least those large plumes, we have now evidence for 3 of them that there are these large ultra-low velocity zones that may be the expression of a very thin core-mantle kind of interaction zone, partially molten, that has higher topography in the center of the roots of the plumes, which is the hottest. And then if you have smaller plumes that don't make it all the way up, you might have a smaller ultra-low velocity zone. So I guess I've already said what I put in these conclusions. I mean, the important part is the new realization about the 1,000-kilometer boundary, which makes us think a little bit differently about the mantle. And this is not just our results. There are other indications for this. There is no explanation from mineral physics point of view right now. People are trying to figure that out. And then I really will insist on the fact that the large low shear velocity provinces are not big, compact features extending very high in the upper mantle, but they're more a bundle of conduits or plumes. So to finish, I just want to say a few words about the future. In order to improve this even more, we need observations in the oceans. This is something I've been working over the last 30 years, with different colleagues, in particular Jean-Paul Montagnier here, and we've never gotten anywhere so far. I mean, very, very little progress in 30 years. Initial ideas were fixed observatories on the ocean floor to complement the distribution on continents, but except for some pilot experiments, it never really got off the ground. There were even several holes drilled by the IODP, one in particular that was going to be a joint Japan-French station on the on the 90 East Ridge. And now the idea is kind of evolving, and because probably inspired by the success of the US array, large US array deployment of dense moving stations, the idea is that perhaps it would be better to install moving arrays that would be install broadband arrays, because you have to have broadband recording, which is the challenge, that would move from one region of the Pacific or the Atlantic in over several years. And you would have to install them for several years in order to capture enough earthquakes. This is Hitoshi Kawakatsu's concept. My view would be you really want to have them as large aperture as possible, as I showed that you need a large aperture, for example, to resolve those very intriguing ultra-low velocity zones at the core-mantle boundary, among other features. There are, of course, other concepts like the Husnolet's floaters, which have some advantages of being able to kind of go wherever they want in the oceans, but have the limitation that you only record P waves, at least for now. And then the other aspect is, how do we improve, given the very computationally challenging computations that we need. I think the future is not in trying to improve the whole global structure, but to focus on some regions of interest, for example, the bays of plumes, and develop methods which will allow to go to higher frequencies. And so we are, this is work by Ider Masson et al. There are other people developing this, in particular in Satish Singh's group, where the concept is to basically only compute the wave field once in a background 3D model, and then confine the inversion to a specific region, which allows to go to higher frequency and do many iterations. So this involves some mathematics. Basically, you have to install what we call mirrors, or time reversal mirrors on the boundaries of these regions. And we are working on this. Just wanted to show a test that was done by Ider Masson here at IPG, who is a postdoc in my group, where he compares, this is a fluid two-dimensional Earth, but a test where he has a target model with some lateral heterogeneities, and he compares the inversion. He has stations and sources all around the Earth, compares the results of the inversion when you do the global inversion, and one where you limit the inversion to the box. Basically illustrating that even if you don't have too much information about the structure outside, the detailed structure outside of the box, you can recover some of the signal inside. So this is it. This is the future, in which we and other groups are working on. And I thank you for your attention.
Non ? Oui, il marche. Je ne sais pas si vous avez besoin du micro pour les questions, ou si vous parlez fort, voilà. Donc, allez-y. Tu peux le même en français, oui, il faut parler fort, fort.
C'est-à-dire, ça peut être les deux, mais l'idée, c'est que c'est probablement de la fusion partielle parce qu'elle a une forme très régulière. C'est vraiment la forme. No. Okay, so maybe I should repeat the question in English. The question is, how do you know, why do you say that these large, ultra-low velocity zone is partial melt? Well, the whole point is that it's based on its shape, that for the first time we can really constrain, because other studies only have one direction usually where they look at, or very small azimuthal range. And we're The same model works, the same simple cylindrical model. Now, I don't know if it's a cylinder. The idea is that it's axisymmetric. Works for different illumination from different sides. So that's the whole point, is that it's very regular in shape. And so it is much easier to explain by partial melt. Say the boundaries would be basically the phase change from partial melt to solid, rather than a solid heterogeneity. But the partial melt could also be enriched in iron. I'm not saying that it's, the same composition as the solid. Mm-hmm. So the question is, what's going on at 1,000 kilometers? We see deflected slabs, stagnating slabs, so that we have difficulty penetrating into the lower mantle, but we also see deflected upwellings, right, which also seem to kind of have to stay there or horizontally and then only move up, so that, again, we can think of the transitions on the bottom of the transition in a kind of extended way, right? Because it starts at 660, but something goes on at 1,000 kilometers. That seems to be pretty clear, that this is like a boundary layer that kind of separates a stagnant mantle from a more vigorously conducting upper mantle. Yes, very much so. But the deflection actually is important, I think, because many studies try to correlate hotspots directly with the structure at the base of the mantle. And that actually doesn't work very well, because many of them are offset. They're not offset that much, but it's still thousands of kilometers. So if you do it naively, or, if you do it naively, it doesn't work, you can introduce mantle wind and then it works better. But the point is, the mantle wind is probably doesn't extend to the whole mantle. I mean, this is something that needs to be kind of considered. Henri? C'est un peu ce que j'ai montré. That's really okay. So the question is, can I distinguish a forest of upwellings, a forest of plumes, from a big fat plume? Now, within those fat plumes that I've shown, I cannot say exactly. I cannot tell you whether that big thing, which is 1,000 kilometers wide in our model, is made up of thinner, multiple thinner conduits. But what I can say, and I think I tried to show it in the tests, in the synthetic tests, is that these are well separated from each other, right? So if you think of the large low shear velocity provinces, they are not compact, low velocity regions, maybe denser than average, extending, as a block. They are made up of kind of isolated features. But the isolated features, we don't have the resolution to say whether they are, they could be like dikes, right? I'm thinking of this in terms of maybe a different kind of rheology for the lower mantle. There could be a series of dikes, very thin dikes, that we cannot resolve, but they are bundled. They would be localized, say. Mm-hmm. Right. The one I showed, this one maybe? Yeah. So,
something striking is that when you are taking the volcanoes basically and you reconstruct them with respect to time, using, for example, hotspot model, you will find elongation bands of volcanoes which seems to fit with the data. So it would be interesting to observe.
yes, I mean, right, because the bands are elongated.
Which remains in time, in past time, this figure would be something that stay historically.
Right, so actually, I'm not sure this is completely true because I didn't show this and I'm not sure I have. But if you look in the Indian Ocean, you also have these things. Of course, here I'm showing already the absolute plate motion on top of, so it's sort of a little bit interpreted, but the black lines are in the direction of absolute plate motion. They have nothing to do with the tomography, right? They're independent. This is Cremer's model. And you can see... Yes, but okay, so let me try and find one more slide. Maybe I have it at the end of this presentation somewhere. Oops, no, I didn't. But in the Indian Ocean, it's not very clear from that figure because of the scale. But can you see this feature here? It actually goes, well, okay. This feature here, which comes from La Réunion, actually travels to the east of India. If you were to look at the kind of ages of volcanism, you would see that there is a change in direction at around 50 million years, and the hotspot track at older ages goes to the west of India. So this is actually a modern feature. It's a dynamic feature of the present time, at least the last 50 million years, but not necessarily further back.
Yeah, that maybe we can provide those. We should compare our data.
Yeah, sure. Okay.
So I was wondering more about general aspects of mantle plumes. So people have considered them for now about 50, 60 years, and they seem to be well established. So what I would like to know is where do you see the future of this field? Like, where should the science go with mantle plumes? I mean, they are there are some little questions, but generally they seem to be there and they seem to be well accepted. And what do you think, what's still left to go?
Well, I think we still want to get higher resolution. In particular, these questions, are they really big, upwellings, or are they made up of smaller scale kind of features, which will help us understand better the rheology of the lower mantle, for the lower mantle. But there's also what goes on in the upper mantle. And right now, we just don't have much resolution to follow them because they become narrower in the upper mantle. So some of them we kind of see, but it would be really important to try and resolve them better to kind of get a better understanding of the relation, how they interact with the secondary scale convection, and how they, and map this secondary scale convection better, I think, and relate that to geochemistry and all of that. So I think there is still, so there's that. The lowermost mantle, the ultra-low velocity zones, for example, I've kind of posited that I think you're going to find big ultra-low velocity zones under each big plume, but I haven't proven it. We have 3 examples. We need to work on that more and, improve resolution. So I think, there is a change with these numerical methods. There is a big change in what we can do in tomography, but it's only the beginning. I think we can do much more. I mean, it's opened up the field to improve the sharpness of images and therefore inform dynamic modeling. Well, I will not, I mean, I disagree with the idea that they arise at the edges of LLSVPs. In fact, there has been at least 2 papers that have questioned this on a statistical basis, and it's very simple that yes, this one. The Atlantic or African LLSVP is very elongated, so anything, any hotspot is on the edge of that, and so that's why you statistically find them there. But if you look here, I mean, I don't know, would you say that these guys are in the middle or on the edges of the LLSVPs? I think the LLSVPs are actually a bundle of things. They're not even the very bottom 200 kilometers. If you look at some of these cross sections, maybe this one, for example, you can see that the roots here are, there's no, not much of an extent of, well, there is more here, but even this is kind of chopped up into pieces. So I'm going to even question, you know, whether the notion of LLSVP is really valid. I mean, it is valid in the sense that from the large scale point of view, it is significant, right? It separates, you know, there's the ring of fast velocities, and there's two portions of the mantle in the Pacific and the Atlantic, but within it there is much more fine-scale structure. And there is another controversy going on, is on the density. And so if you talk to one seismologist, they will say, no, we can explain everything by just thermal structure, thermal anomaly in the LLSVPs, and somebody else will say, some other studies will say, no, they are denser than average. And I think it's actually, these two should agree because they're not sampling the same part of the enormous mantle. The studies that claim that LLSVPs are denser than average actually have more resolution at the very base, maybe the last 100 kilometers. And those that are based on travel times that think you can explain everything with just thermal, they just don't sample that region. So it could be a rather thin region of denser material. Maybe chopped up into pieces, I don't know.
But then, because perhaps this is stupid, but by mass balance, how long would it take to empty this low velocity zone by extracting the material in the plume? Did you make this calculation? If it is so,
but if it's okay, so if it's a core-mantle interaction zone,
so it's continuous.
It could be continuously.
No, but you could check that by just.
That's a good question for, you know, geochemists, I think. Yes.
In the Pacific, so you are showing us some mostly vertical structures, less hotspots. In the Indian Oceans, the things may be quite different. So because the anomaly that goes from the South Africa to
Yes, so there is a big. This one. So what you have to be, first of all, the resolution under Africa is not as good as under the Pacific just because of the distribution of earthquakes and stations. And there are indications that even this large structure is broken up. There are some studies, you know, travel time studies that show that you have some intervals in between. It certainly looks very massive here, but I wouldn't be surprised if, you know, in the future it was shown that that this is not a compact structure. But it may be, I mean, it may be. But it's still not, you know, the whole area. It doesn't cover the whole area.
Ok, est-ce qu'il y a encore des questions? Non? Bon, donc merci encore. Donc vous pouvez continuer à poser des questions à Barbara au buffet dans la médiathèque.